Happy holidays, and welcome to a holiday edition of Science Matters, part of the Origins podcast produced by the Origins Project Foundation. This week we released a podcast which was really about wishful thinking with an author I really enjoy, Augusten Burroughs, and I thought it would be fun to supplement that since it's the holiday season and often produce a Science Matters around that time to talk about another aspect of what has been wishful thinking. But now may be turned into a little more science than just wishful thinking. And it also allows me to do two things: to tell you a holiday story about our origins, and also to cover a topic that's been in the news currently this month and a lot of people have asked me about. So let's go right to the presentation. I'm going to start sharing my screen. And here we go. So the title of the presentation is How the Universe Made Your Holiday Gifts. And we'll go almost right back to the beginning of time. And it's got a kind of a subtitle, which is, and the gift that may keep on giving. And that's the topic that is more relevant to what's going on right now in the news. So I want to begin with a quote which I've adapted from a famous quote. The quote I want to use is, if you wish to create a holiday gift from scratch, you must first invent the universe. And that's after the famous quote from Carl Sagan, who once said, if you want to create an apple pie from scratch, you must first invent the universe. So if you want to create your holiday gifts, first you have a universe in which they can exist. And then let's assume we've already invented a universe, okay? And we have one. What next? Well, we have to make the stuff that your holiday gifts are made of, all the matter that we look around us, on Earth right now that we use for our holiday gifts. And that matter, those elements, began to be made in the first few moments of the Big Bang. When the Big Bang was very, very hot, in the earliest moments of the Big Bang, before the universe was 1 second old, the universe was a dense gas of protons and neutrons and electrons and neutrinos and photons, and there were no elements. There were no light elements. But as the universe cooled below about 10 billion degrees or so, and the universe was a little older than 1 second old, back down to about the time it was a few minutes old, what happened was a set of nuclear reactions occurred, which turned protons and neutrons into some light elements. Not all the elements, but the light elements. And I show here a number of these nuclear reactions. Protons and neutrons, when they collide together at high temperature, can every now and then collide and combine to form the nucleus of heavy hydrogen called deuterium. That nucleus contains a proton and neutron. And since the proton and neutron are bound together in deuterium, a little energy is released when the proton and neutron bind together. Every now and then that deuterium can collide with another proton, producing a nucleus that has two protons and one neutron. That's the nucleus of a new element, helium, but not the helium we're used to, which has two protons and two neutrons. This one has two protons and one neutron. And again, in the process, some energy is released. Then every now and then, two deuterium atoms can collide together and produce helium-3, and one of the neutrons in this combination gets released, or they can combine together to form not helium-3, but hydrogen-3, another name of which is tritium, hydrogen that contains one proton and two neutrons. In that case, another proton is released. Tritium is actually unstable. It has a lifetime of 12 years or so. But every now and then, the helium-3 that's produced can collide with deuterium to produce helium-4 plus release a proton. And every now and then, some of the tritium that's there can also collide with deuterium to form helium-4 plus a neutron. And these processes happen as the universe cools down, releasing a fair amount of energy, but what that does is convert protons and neutrons into helium. After helium, there's a gap, and the universe can't really effectively go to the next step of making much heavier elements. There's some small amount of the next element created, lithium, in this process by another process that converts deuterium and protons and neutrons into helium, but in the process some lithium is produced. So the only elements that are produced in the Big Bang are hydrogen, the next lightest element helium, and lithium. About 25% of the universe is helium, and we can actually calculate that. We can use the rate of nuclear reactions and the temperature of the universe that expands to predict how much helium we produce. Now, in the process of producing helium, of course, you produce deuterium. But the more efficiently you produce helium, the less deuterium is left over, because deuterium is a product that's used and burned into forming helium. So if you can do that very efficiently, there'll be no deuterium left over. And so the more helium you produce, the less deuterium will be left over. We can make these predictions then about how much helium will be produced in the early universe, how much deuterium will be left over, and also how much lithium would be produced. And here are the predictions. And as I've often said, I use these predictions to tell people that the Big Bang never happened. I do have this image that you can now see in my wallet, a wallet card. And when people tell me they don't believe in the Big Bang, I flash them this image, because these are the predictions based on first principles of nuclear reaction rates of how much helium would be produced in the first few minutes of the Big Bang. And of course, the amount of helium that would be produced depends upon the number of protons and neutrons in the universe. If you have more protons and neutrons, you'll end up with more helium. Then you see the amount of deuterium that would be left over that wasn't quite all burned to form helium. The more protons and neutrons you have, the more efficient you are in producing helium, and the less deuterium that's left over. Similarly with helium-3, and then there's some lithium produced. And you notice these numbers change. 25% of the universe is helium, to predict to be helium more or less, whereas 1 part in 10 billion of the universe or so is predicted to be lithium, and about 1 part in 100,000 or so, or 2 parts in 100,000 or so, is predicted to be deuterium. What's amazing is when we measure the actual abundance of primordial abundance of helium and deuterium and lithium, we get numbers that agree very well with the predictions. And this varies over 9 or 10 orders of magnitude. One of the reasons we know the Big Bang really happened. And that this process of primordial nucleosynthesis, Big Bang nucleosynthesis, really happened. Now, of course, to go from these light elements that are produced in the Big Bang to the elements that make up your gifts, you need stars. And stars have nuclear reactions in their center until between the time of that this process ended of producing helium, but when the universe was about 3 to 5 minutes old, until the universe was a few 100 million years old, no more nuclear reactions took place. But then when the universe was about a few 100 million years old, and we're going to try and look back to that time with the James Webb Space Telescope, the first stars formed. And stars are nuclear furnaces, stars like our sun. And to heat up a planet, in order to keep it going and have holiday seasons, you need a star like the sun. And inside the sun, the temperature is only about 15 million degrees, not 10 billion degrees or 15 billion degrees. But nuclear reactions do happen in the center of the sun. Nuclear reactions that are very similar to some extent to the reactions that happened in the first few seconds of the universe, except the sun is made mostly of hydrogen, and it doesn't really have those initial neutrons to work with. Remember, in the early universe, there were more or less roughly when the universe was 1 second old, almost as many neutrons as protons. But in the sun, it's just made of protons. So the nuclear reactions are slightly different. But they happen. That's one aspect of what makes it difficult, the fact that the sun is made of just protons and the fact that it's not as hot as the early universe. And because it's just made of protons, the reactions happen very slowly, both due to the temperature of the center of the sun, which sounds like 10 million degrees or 15 million degrees may sound hot, but not on the scale of nuclear reactions, but also because of the weakness of the forces involved. And the interesting thing is, if you actually look at the energy production in the sun, it's only about 0.3 milliwatts per cubic centimeter. During that time, each hydrogen nucleus waits for about 9 billion years before it initiates a fusion process, which is one of the reasons our sun will keep burning for almost 10 billion years, because most of the protons of the sun aren't fusing together to produce helium and release a lot of energy in the process. But this zero 0.3 milliwatts per cubic centimeter is not very much. It's actually only about 1/4 the amount of heat power your body generates while you're reading what's on the screen here. But of course, the volume of the sun is much bigger, and it adds up. And when you add up all of that energy over that volume, it's enough to heat the earth and to ultimately allow us to celebrate holidays and to make our holiday gifts. Now, here's the reactions that occur in the sun. The first reaction that occurs is when protons and protons collide with other protons. Most of the time, nothing happens. But every now and then, due to the force we call the weak force, a proton and a proton can collide and turn into a proton and a neutron, which of course form the nucleus of deuterium, what I had in the other diagram called H2, I now call D2 because for deuterium. And in the process, that releases a particle called a neutrino. It also releases a particle called a positron, but that positron will collide with electrons in the sun and produce a lot of energy. So the net product of two protons and an electron will be the nucleus of heavy hydrogen, deuterium, plus a neutrino, plus a certain amount of energy. This is 1.442 million electron volts. Now, the amount of energy released in a standard chemical reaction is of order electron volts. These nuclear reactions release 1 million times more energy, which is one of the reasons that nuclear reactions are ultimately related to nuclear bombs, which are so powerful. But this releases a lot of energy, and this is the process that's largely powering the sun. The problem is it happens very, very slowly, and it's not yet complete. It happens very, very slowly, but once you produce deuterium, then deuterium can collide with hydrogen, with basically a proton again, and now form helium-3, as we've seen before, just by a proton, neutron, and a proton combined together to form a nucleus with two protons and a neutron, the nucleus of helium-3, in the process releasing a lot of energy. And finally, we have two helium-3 atoms, nuclei, I should say, will collide together to form the nucleus of regular helium, helium-4, which is very, very tightly bound, and it will release two protons in the process and release the most energy of any of these processes. And basically, and the first person to recognize these reactions might occur was Hans Bethe, who first began to calculate this in 1939. Around the same time, he was thinking about being part of the Manhattan Project to develop a nuclear weapon. He was thinking about the process of the power of the sun. And basically, what you have is four hydrogen nuclei, 4 protons, eventually, by the reactions I've now shown you, producing deuterium, and then helium-3, and then helium-4, and releasing in the process over 20 million electron volts, about 26 million electron volts. And here's the rate at which these reactions occur. This process takes almost 1 billion years. But once you produce for the average proton, obviously some protons interact more quickly. But once you create deuterium only survives about 1 second in the sun before it interacts with a proton, forming helium-3. And then the helium-3 atoms survive about 400 years on average in the sun before they collide to produce helium-4. And in the process, as I say, you release 26 million electron volts of energy, about 26 million times the energy associated with any atomic reaction, any normal chemical reaction. This process powers the sun. It will keep our sun going for almost 10 billion years. And it's the reason we can have a holiday in the first place, these kind of nuclear reactions. Now, let's go to the gift that keeps on giving. Well, our sun is certainly the gift that keeps on giving. But there's one we're trying to create here on Earth. On Earth, for a long time, we've recognized these fusion processes in the sun, and we want to try and produce power that uses the same kind of process, just from hydrogen. And the world has a lot of hydrogen in the world's oceans, among other places. And if we can ever use hydrogen-induced fusion to power the world, then we'll have basically, effectively, almost an infinite amount of energy. And there are many other advantages of this. First of all, we have lots of hydrogen. The second advantage of these kind of reactions is they don't produce any carbon dioxide in the process, or any heavy radioactive materials like fission reactors do. So a fusion reactor would use just hydrogen or isotopes of hydrogen as a fuel, would produce energy, lots of energy, and it wouldn't produce CO2, therefore not leading to or exacerbating global warming. It's kind of the holy grail of energy production from the Earth. It's wishful thinking, and we love to wish a fusion-powered reactor into existence. Now, there are various difficulties associated with creating a fusion reactor that have been known for a long time. First of all, you have to produce hotter temperatures to have fusion occur quickly enough to actually see it. And remember, in the sun, the average proton just takes 1 billion years to interact, and we don't want to have that happen for a small amount of material in a fusion reactor. And therefore, you need to have much hotter temperatures, but between 100 million and 1 billion degrees. And you can't use just plain hydrogen. Or in fact, we don't need to use plain hydrogen. We can try and use other things, as we'll talk about. Well, we want to remember the reason things are so slow in the sun is that we're relying on the weak interaction to turn 2 protons into the nucleus of deuterium by turning one of those protons into a neutron. That is a very slow process. So we want to look for nuclear reactions that don't require changing neutrons into protons or vice versa. And the nuclear reaction with the largest probability of happening, if you think about the isotopes of helium, it's almost 100 times greater than any other reaction, is just the following. If you start with deuterium, heavy hydrogen, and some tritium, even heavier hydrogen, this has a proton and a neutron, this has a proton and 2 neutrons, you can create the nucleus of helium-4 directly, releasing a neutron and a lot of energy. And because you're not turning any protons into neutrons or neutrons into protons, this reaction is mediated by the strong force, which is much more quick. And therefore, the idea is, let's start with fuel that's made of deuterium and tritium and see if we can turn it into helium, releasing the kind of energies characteristic per reaction of what's happening in the sun and allowing us to power fusion reactors that will power civilization for a good long time to come. And that's been the holy grail. That's been the wishful thinking. Now, recently in the news was a new announcement from the National Ignition Facility, part of the Lawrence Livermore National Laboratories, a security facility in the United States. That facility, and I've visited the National Ignition Facility, it's immense. It's the size of 3 football fields. It's got 192 of the highest power, highest energy lasers in the world, all focused on a small millimeter-wide metal cylinder that holds a capsule the size of a peppercorn, and that capsule contains deuterium and tritium. And the idea is, if the lasers impinge on this, maybe they can generate temperatures in that target of more than 180 million degrees and very high pressures, causing fusion. And the idea is to create some kind of controlled fusion reaction. And what was just announced a few weeks ago with great excitement and fanfare by the National Ignition Facility and then by the Secretary of Energy was the first time that this facility achieved ignition. Now, what do we mean by ignition? The process that they try and do is to have these lasers impinge on fuel pellets from all sides perfectly spherically, releasing hot X-rays that create a shock wave, a spherical shock wave that causes that pellet to implode, making its density far, far higher and reproducing temperatures of hundreds of millions of degrees, and then hoping that fusion reactions will happen inside that hot, dense pellet, releasing heat and energetic neutrons. This, by the way, is the same process that powers thermonuclear bombs, but not with lasers. The way most thermonuclear bombs, often called hydrogen bombs, work is by having nuclear fuel like this or something like this, and then compressing it down by first exploding an atomic bomb, a normally fission bomb. And then the difference here is that in this case, the energy release is controlled, and it's also far smaller than in a nuclear weapon. You'll see how much energy is released. On December 5th of this year, at 1 in the morning, the first ignition ever happened. And what does ignition mean? Before this, scientists at both the National Ignition Facility and other places had produced fusion reactions, but they kept putting more energy in than came out. And in this case, what you want is a system to create enough energy to keep itself hot and ultimately produce more fusion reactions, and therefore release more energy out than comes in. So ignition comes when you're basically having a sustained set of fusion reactions in that small pellet, and the system is retaining its own heat beyond the heat that's imposed by the lasers. And on December 5th, 2022, um, it occurred a collision, a shot of the laser into one of these pellets occurred, and 2 megajoules of energy was input into the pellet, and 3 megajoules of energy was released. Now, megajoules sounds like a lot, and it is on many scales. It's enough to boil a few kettles of water, which may not sound like a lot, but now remember, you're talking about a very, very small pellet of material that's releasing enough energy to boil several kettles of water. And if you had enough of that material, one hopes in the future one might have enough to boil a lot of kettles of water for a lot longer time, and use those to generate electricity. That's the goal, the Holy Grail. But the first step was taken for the very first time at this facility. More energy came out than went in, and that's what was heralded and on the front pages of papers around the world. And I want to just go into it a little more detail. The first thing to realize is that this process of taking these deuterium and tritium pellets and compressing them to produce energy it does not produce a workable power plant for a whole bunch of reasons. First of all, it's true that 2 megajoules of energy was impinged upon the pellets, but the lasers actually, when all the lasers shot, they took 300 megajoules of energy to produce the shot. So in fact, in order to get 2 megajoules of energy, you had to start with 300 megajoules of energy if you want to get 200 megajoules of energy impinging on the pellet. This system has less than a 1% efficiency. So yeah, 3 megajoules came out of that pellet, but that's less than 1% of the total energy used by the facility. So that alone doesn't make it a practical power plant. But there are other reasons. At this point, the facility can be set up to shoot 1 shot per day, 1 pellet, 1 shot. If you want to have a commercial reactor, you'd need at least 10 shots every second to kind of produce the kind of energies one needs for a commercial reactor. And so that's almost 100,000 times faster than they're able to do right now. And it's even worse. Right now, each of these pellets costs about $100,000 to make. In order to power a reactor, you'd need maybe 1 million or so of those pellets to power a power plant. So you see that while this is a remarkable technological feat that's been achieved, in no way does it in any way associate with a practical fusion reactor at this time. And it's important to realize that in fact, what wasn't emphasized in the media, but should have been, is that the experiment wasn't done to generate power or to even have its prime purpose looking at ways to generate power. It was actually an experiment as part of our stewardship of nuclear weapons. Lawrence Livermore Laboratory is one of the laboratories that helps build and maintain nuclear weapons. This experiment was designed to allow the testing of the science related to nuclear weapons and the stewardship of nuclear weapons stockpiles. One of the reasons is, and this is a good reason for those of us who like to not to have underground nuclear weapons explosions happening now after that treaty from many years ago. Many people had argued that in order to know that our nuclear stockpile works, we have to every now and then explode a bomb. And it was argued that if you could create a facility that would develop fusion reactions, you could test the technologies we use to produce fusion, and also produce conditions that would allow us to test the materials that are used in bombs without ever having to explode bombs. So the purpose of this facility was not primarily to create power, but to allow us to basically test the science of nuclear weapons. And it did that. It was performed, after all, in fact, it's important to realize it was performed by the National Nuclear Security Administration, not by the Department of Energy Office of Fusion Energy Sciences. So it wasn't primarily for fusion energy. It was to help understand our nuclear weapons stockpile. Nevertheless, the physics of this is relevant, and having been able to do this helps teach us more about how we might ultimately produce fusion energy. But hope springs eternal, and that's what I want to say in this holiday season. It's true that fusion power, the goal of fusion power, has always been at least 25 to 50 years in the future, and that's been time invariant. 25 to 50 years ago, it was 25 to 50 years in the future, and today it's probably 25 to 50 years in the future. Certainly, it would be at least that if we just had the National Ignition Facility. But there are other fusion technologies aimed at producing power, not aimed at checking nuclear weapons. And one of those projects is now called ITER, one of the largest collaborative science projects in the world. It uses something called magnetic confinement to heat a plasma of hydrogen or deuterium and confine it and heat it up to the temperatures characteristic of the temperatures inside the sun or greater. That magnetic confinement torus is called a tokamak. And those have been built and tested, and as I'll describe in a moment. But the ITER is a 35-nation collaboration that's building this multi-billion-dollar test facility in France right now. It's designed to eventually yield 500 megawatts of power, using 50 megawatts of input heating to power the tokamak. Previous tokamak, called JET, which was the one that was built before this, in 1997 produced 16 megawatts of fusion power from an input of 24 megawatts. So you see more power was put in than taken out. But this technology has allowed fusion to happen. It's just more power is put in than comes out. So you don't have that kind of sustained reaction. And it certainly wasn't practical as a power plant. But ITER, which will begin to operate hopefully in 2025 and may use some results over the next 10 years, is designed to actually produce enough power to be potentially a practical, at least a physically practical nuclear power plant. Remember, it costs $10 billion right now, and that's a little much for producing economically viable power plants. But this research continues, and there's a picture of a tokamak with the toroid in the center, with huge magnetic fields and solenoid magnets, superconducting solenoid magnets that compress that hydrogen and heat it up, and that plasma to super hot temperatures, hotter than the temperatures of the sun. And if we're going to have fusion power, it's more likely to come from this technology, from the other technology. But it's decades in the future, at best, as it always has been. So the new result shouldn't. It's incredibly exciting from a scientific perspective and from a national security perspective, and it teaches us about how fusion reactions occur and how they might, in principle, be promoted here on Earth. But it's not yet anything. It's not yet ready for prime time. Having said that, of course, hope does spring eternal, because we still have that amazing furnace in the sky called the sun, which operates on the same set of nuclear reactions. And 10,000 times more energy is impinging on the Earth every day from the sun than humanity currently uses. And if we could exploit that much more efficiently, the sun itself can help power the needs of civilization for now and into the future. And so while it's important to look for creating fusion reactions here on Earth, it's important to realize that we have tens of billions of fusion reactions going off in the sun for free. And if we can just exploit some of that by converting solar power to electricity, for example, we'll help meet the world's energy needs. And so I just want to say that since hope springs eternal and science continues to progress, we'll continue to look for new science and new technologies that help civilization and that help us understand the universe from the beginning of time through stars and into the future. So happy holidays to all of you from all of us, and at the Origins Project and at the Origins Project Foundation. And I think I'll come back. That's what I was looking for. I want to come back to say to all of you, have a wonderful holiday and a wonderful new year. We've got a great set of podcasts online for the new year, and a great set of projects that we're involved in at the foundation, and we're in the process of preparing our next travel experience, which will be to the Galapagos Islands, and we hope to advertise that and open up spots for that with two remarkable, wonderful scientists and communicators, Franz de Waal, the primatologist, who I've had a podcast with, and Elizabeth Colbert, who the Pulitzer Prize-winning writer, who I have just recorded a podcast with, which will release in the new year. So it'll be an exciting new year for all of us, and I hope all of you have a happy, prosperous, and healthy new year, and stay safe. I hope you enjoyed today's conversation. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit originsprojectfoundation.org.